Okay, so we'll continue with Tom's lecture on algebraic quantum field theory.
Okay, thank you very much. Okay, so we left off last time with some information about the classification of type 1, of various types of von Neumann algebras. And that was based on a couple of things: the projection, possible projection operators in the von Neumann algebra, and the possible states in the von Neumann algebra, in particular the traces. So today we're going to start by talking about purifications of those states, right? So what I mean by that, I remind you, we have some algebra we're going to think about. So this is our von Neumann algebra. And it's always a sub-algebra of all possible operators on some Hilbert space. So it's acting on some specific Hilbert space, and it's some sub-algebra. And a purification is just, a state, remember? A state was a linear functional which takes A to C and has positivity properties and other things. So specifically, we need it to be normal and positive. And we talked about those before. And so in particular, purification is one where I find a vector in this Hilbert space. And I take that vector and I create some expectation values with that. So this is just some, meant to be some notation where I'm sort of thinking of the state as waiting for some operator to feed in. And you think of this as restricting to A, right? So in principle, I could feed in any operator into this state in B of H, but I'm just going to restrict to A, and that defines my linear functional. And a purification is a psi such that this is true. So I start with a row, and then I find a psi where this is true. Okay? And so if I have a purification, then I can, if there's another purification, where I just take a unitary in the commutant, right, the set of all operators that commutes with A, and I just act with that on psi, and it's very simple to see that that induces a state that's exactly the same as rho, right? Just because U is unitary in the commutant, so you can sort of pass it through operators here, just cancel it out. Okay. All right, so now, okay, so we have these purifications, and now it's important to talk about properties of these purifications. So we already mentioned this in the finite dimensional case, but let's go over this now in the infinite dimensional case. So there's two things we have to think about, whether the wave function psi is cyclic or separating, or both. And so cyclic just means that if I take A and I act on the purification, psi, then I should approximately get all of the states in the Hilbert space. Now, we don't necessarily get everything because we're in infinite dimensions. In finite dimensions, we could sort of get everything with this. But instead of that, we can just demand that we get almost everything, which just means that it's dense. So if I take the closure in the Hilbert space norm, then I get all of H. Okay, so this is sort of a useful trick. If I want to talk about any state in the Hilbert space, I can just take a cyclic state and act with some operator locally, and I'll approximately be able to approximate it to arbitrary accuracy. Okay, that's what that's saying. And the separating property is the statement that if this vanishes, then A has to be trivial. Okay, so there's no operators in the algebra that annihilate the state. Okay? And as we discussed in the finite dimensional case, these properties are related to the density matrices and sort of how entangled the density matrices are. So if they're invertible, then you get these things. Yes. No. So this is like additional properties that we want to, maybe impose. Okay, so it's like, these list of things that you add, you may or may not want to add them, but this is something we can say. So if we have a state here, then we might look for a cyclic and separating state. Now, one thing we did talk about is that rho, if rho is faithful, then the purification will always be separating. And this is an if and only if statement, right? So if you started with a state that's not faithful, remember faithful is the statement that if I feed in a positive operator and it gives 0, then that had to be 0, right? So this is the faithful condition. And so this is sort of related to the separating condition in this sense. So you will never be able to find a purification that's separating if it wasn't faithful to begin with. Okay? Okay. All right. Good. Said that. Yeah. So now we sort of want to specialize to this case of cyclic and separating states. So we're going to make that assumption. So it depends on the purification. So some purifications may be cyclic and some may not be. Okay, so it's not intrinsic to rho. So I can't tell you, I can't give you a definition. Yeah, in terms of rho, it depends on the purification. Okay. So depends on psi. Good question. Yeah. Are there any other questions? Sorry, I haven't been very good questions so far. Questions from last time? Yeah. Oh, sorry? Yeah, so I didn't say it, but this is another purification with a unitary, but this could also be an isometry. And with the isometry, you can change that property. Yeah. So yeah, that's a good question. Yeah. Yes.
A naive question: what do you mean by a positive operator here? Because we usually define in quantum mechanics a positive operator as yeah.
Good question. Yeah, a positive operator is just an operator that in any state in the Hilbert space, this is positive.
Isn't the definition of rho a bit circular then?
Sorry?
Isn't the definition of rho a bit circular then?
What do you mean circular? So I didn't define positive here because I defined it last time. Do you want me to define it? Or yeah, that's just the statement that if I feed in a positive operator, I get something positive. Now, it need not have been positive. Okay, so let me give you an example of a linear functional that's not positive. That's just this linear functional, right? Where I take two different states here. That's not a positive linear functional, and it's not what we usually think of as a state, right? So that's what I mean. Okay? So it is, it's important to add. Yes. Yeah. Okay, so it is defined with reference to the von Neumann algebra, and the von Neumann algebra is defined with reference to the Hilbert space. So there's that sense. But actually, you're saying just because of this condition? Yeah, like the positivity. You can make these things independent of the Hilbert space, but it's kind of annoying. Yes. Yeah, that's also a great definition. Yeah, AP is some Q dagger Q. Yeah. Good. Yep. Yeah, that's true. Yeah, it's true. Yes, you're right. This is independent of the Hilbert space then. Yeah. Okay, thank you. Yeah. Good. Other questions? Okay, yeah. Yeah. So if the purification is separating, then it came from a faithful state. Yeah, that's right. So this is any operator, but when you actually go and derive the faithful condition, it's A dagger A that comes around, right? So that's positive operator. Yeah. Okay. Good. All right. So yeah. So this case is important, cyclic and separating. So we already talked about a situation where it comes up, right? So this was in the type 1 case where we have matrix algebras acting on finite dimensional Hilbert spaces. If we had this canonical purification, and it's sometimes also called a standard purification, then we have cyclic and separating, okay? But that seemed a little bit contrived, right? That, we would always work in such a purification, like if you look at quantum information, people, they would never like specifically work in that purification. However, when we go to these other cases, in particular, when we talk about quantum field theory soon, we'll see that this is sort of the generic situation. So generically, we'll have cyclic and separating states. And so, what I'm going to say is quite general. Okay, good. Right, and we'll talk about why that is, but that's because of this Riesz-Leiter property. Okay, so another thing that I want to mention is that there's a relation between these properties for psi and the commutant. So if we ask about whether the state is cyclic and separating for the commutant algebra, right? So whenever someone says cyclic and separating, they need to give you two things, the wave function and the algebra. And so if we do it the same thing for the wave function and the commutant, then there's some relation between these two. In particular, if I talk about the commutant, then psi is cyclic if for A, psi is separating, and psi is separating if psi is cyclic, right? So there's some like symmetry between these properties. Okay, and yeah, and this is actually not very hard to show, but I'm going to skip it for time. But if you look at my notes, you can see an example of how to show this correspondence here. Okay. What's that? Some prime. That's a prime name. Yeah. So yeah. So as I said, yeah. So these are two different things. So it's, psi is cyclic for A prime. Psi is separating for A prime. That's what I mean here. Is that clear, or that's not very clear? Okay. And so yeah, similarly here. Okay. All right. So now we have a cyclic and separating state. What we're going to do is develop modular theory. Okay. So that's the next step. Okay. And I should say from the outset that you don't need cyclic and separating states to develop modular theory. It's just much nicer. Okay, so there's some details that we can ignore here. Yeah. Yeah, it's a state, yeah. Yeah. I never said anything about GNS. Did I say anything about GNS? I don't think so. Ah, okay. Well, okay, so all I'm saying is someone hands you a state in this form, you can try to find a purification, okay? You may or may not succeed, but so you can try to find a purification on your Hilbert space, and then that's what a purification is. Okay, and then there's a set of these, and you can try to classify them and add certain properties. Okay, that's all I'm saying. Okay.
You may not succeed because.
Yeah, because the purifier might be too small, right? So it turns out that once you have a cyclic separating state, you always succeed. So yeah. Okay, good. Okay, so modular theory. Okay, so I'm going to define some operators that are meant to get at these modular operators that I talked about last time. And as I motivated, they're the things that sort of take over for density matrices when we don't have density matrices. Okay, so I define an operator I'll call S, which takes the state A psi to A dagger psi. Okay? And because there's this sort of symmetry here between A and its commutant, it's also useful to define another operator, F, which acts on A prime psi and gives me this state. Now, in this form, we've actually defined S and F are unbounded operators, at least in infinite dimensions. And so there's some trickiness with unbounded operators. So we sort of have to address that. In particular, we would like to do things with these operators that we can usually do with any operator, right? Like many operators we're used to in quantum mechanics and so forth. We can do things like take functions of those operators or do some spectral decomposition of that operator. Okay, and so in order to do that, with these have to satisfy certain nice properties. So in particular, so they're unbounded. We're aiming for nice unbounded operators that satisfy the properties that they're densely defined and closed. And once we have these conditions, which I'll sort of give some hint at what they are, then we can do the usual things with these operators that we like. Okay, and so that's the point here. And so densely defined is sort of self-evident. It means that it's defined on a dense set of the Hilbert space. And indeed, that was one of my conditions, right? Cyclic means that this is the statement of density, right? So now it's an unbounded operator. That means it can't be defined on every vector in the Hilbert space. If it was defined on every vector in the Hilbert space, you can show it's bounded. So there's some things which it can't ever be defined on, right? And so that's sort of called the domain of this operator. Now, right, so that's densely defined. I'll try to say what closed is in a little bit. Yeah. Yeah, so psi is cyclic and separating, yeah. Yeah, you can develop modular theory without that, but that's not what I'm doing here. Yeah, just any vector will work. It's not as nice though. Modular theory is not as nice. You don't get all the very nice things. So usually you'll want this. Okay, good. So in particular, they're densely defined, so we define their domain. A psi, the domain of F is just A prime psi. Okay, and it's not hard to show that F and S are related. So F is equal to the adjoint of S, at least on this dense domain. So this F is defined on A prime here. So on these states, you have F as the adjoint, right? And so this uses the adjoint of an operator. These operators are antilinear. So you need the adjoint of an antilinear operator, but once you have those definitions, it's really easy to show this. It's in my notes, but I won't go over it. And so that's true on this domain, but it turns out the adjoint is defined on a larger domain. Right, so there's some domain that the adjoint is always well defined on. And so you write, actually what you write is that F is, S dagger is an extension of F. So this is what you write when they're equal on some domain, but in general, one is defined on other things as well. And so actually, similarly, you can show S, this guy, and this means that S and F are, this implies that S and F are densely defined and closable. Right? So that means there's an extension. So closable means there's an extension which is closed, which is this nice property that I haven't defined yet. So then we introduce the closure. And so this is the smallest closed extension. And just to define what closed is, S is closed if the subspace, the following subspace, HS, which is just given by the following, for all, sorry, this is either in the domain of S. So this is some subspace of this Hilbert space. And if this thing is closed, if this subspace is closed, then this is a closed operator. Okay? So these operators, as I said, are nice. And in particular, you can use this to show that there is a closure. There's a smallest closure. And in particular, that's what we're going to work with. Okay? So one way to define this closure is just to take two adjoints. Okay? So then that's the closure. And so this is one of our operators. And yeah, so good. All right. And we can do the same thing for F. Okay. All right. So now that we've defined these operators, we can do nice things with these operators. So the first thing that we're going to do is we're going to apply a polar decomposition. Yes? Yeah, that's right. Yeah. That's always, yes. It may not, yeah. So it may not, if this is densely defined, then it's closed. If that's not, then this won't work. Yeah. All right, so good. So the polar decomposition is just, you know, the usual polar decomposition for operators. So you've probably heard of this for matrices. If I have an arbitrary matrix, I can always write it as a unitary times a positive operator. Okay, so we have the same thing here just because of what we just showed. So S bar is J delta to the half, where J is not a unitary, J is an anti-unitary operator. And delta is a positive operator. Okay, so that's the polar decomposition in this form, and we're allowed to do it now. So, and in particular, S bar dagger S bar is delta. Okay. So these things that I'm quoting don't work if you don't have a closed operator. So yeah, so it's basically a nice class of operators that are unbounded, right? And yeah, good. And so we have that in this Tomita-Takasaki theory. That's sort of the basis of it. Okay, good. Now, oh yeah, so J is an anti-unitary operator. What does that mean? Well, let me just define it. It means that if I take the inner product between these two states, I get the same inner product, but I have to flip the order. Right? because it's anti-unitary. Okay. Good. Okay, so now, based on these definitions, you can show various things. So one thing that's obvious is if I have S bar and I apply it twice, I just get the identity, right? Because at least on this domain, I've defined it to give back a dagger. So if I do it twice, I'll just get back a. Right? So it's the identity. And so this has various implications. So I'm just going to quote them so you can see the derivation in the notes. So let me just write some simple implications. So the first one is J squared is the identity. That's different from J being unitary. That just follows from here. And there's some commutation relation between J and delta. So in particular, if I switch the order, I have to change the power here. Okay? And then the final properties that are important are that J leaves invariant the defining state. So the defining state was psi, and so this is the case. Okay? And so does delta. Okay? Now, okay, so at this point, maybe some of you are lost in this math because, yes, it's not totally standard to learn about these bounded operators. But I encourage you to go through the finite dimensional case and just check all of these identities. Okay? It's very useful to do that. That's where you can sort of understand what's going on. So if there's anything that confuses you, you can just go to the finite dimensional thing, look at all the identities and make sure it's true.
Цвети за фризер инструмента в финала. Окей ли е да ядеш месо с стати, понеже там порцията са за двама човека и не мога да индивидуално да приготвя?
I can't understand. Maybe try speak, I don't know, louder or something. Hello? Okay, well, if you can try again later. You had a question? Yes.
So, presumably there's a lot of cyclic and separating vectors. There's nothing unique about it. So if I just happen to choose a different one, would I end up with a different J and delta?
Yeah, you would. So good, that's a great question. Yeah, so the first point is typically once you, so it's true, once you have one cyclic and separating vector, then you have many. The other thing is, yeah, so if I pick a different state, I will get different data. In particular, delta will always be different, but J could be the same in some situations. So I'll mention that.
Are there sort of equivalence classes or just?
There's a nice thing, there's a cone. There's something called a cone, and I'll define what that is, and then you can ask more if you, at that point. Okay, yeah. Yeah, so good. Yeah, so you might have tried to just extend the operator directly on the Hilbert space. But yeah, that doesn't work because, as we said, this is, yeah, so what's the right way to say this? Well, okay, this is the definition. The reason for the definition is these theorems that I'm not telling you. So because of this, this sort of definition of closed on this is called the graph. This closure on the graph, which is this direct sum of the Hilbert space, that is nice because then you get all these things like polar decompositions and spectral decompositions. And I'm not going to go through that. Yeah. Is there any better thing I can say? It's not complexifying the Hilbert space, I don't think. Well, maybe you could think of it that way, but I don't think that's the reason for it. Yeah. The other factor, sorry? Yeah, it's like a graph, exactly. It's a graph, yeah. Right, yeah, you have X and Y, right? And you can think of a graph as X, F of X, right? Which is like this. That's what this is. Yeah, and yeah. Okay, good. So, all right. So those were some trivial consequences. There are some non-trivial consequences that I won't derive. The first one is that there's a nice flow that you get from this, which is just defined by conjugating an element in the algebra by these modular operators. Okay, so I can just do that. So yeah, so delta is a positive operator, right? So I could write delta as e to the minus k, say. And then this is just like time evolution, right? So e with respect to k, e to the I, k, t, a. And so that's all we're doing here. And this flow is called modular flow. Modular flow. And it's a non-trivial consequence of Tomita-Takasaki theory that this flow takes elements in the algebra to elements in the algebra. Okay, so this thing is in A. Right? And the reason that's non-trivial is because how I've defined delta is not an operator in the algebra. Okay, it's definitely not. But when I do this conjugation, I get an operator in the algebra. Yeah. Yeah, because it's an isomorphism, so I can invert it. Right. So if I apply alpha minus t, right, that's the inverse. So yeah, so that's why it's not a subset. Yeah. So good, yeah, good question. Good. And then the other consequence is that if I take J instead and conjugate by J, I get the commutant. Okay, and it's unitary, so I get everything. And you know, these things are non-trivial, but they're totally clear from finite dimensions, and we actually went through them, right? Like it's sort of just obvious in finite dimensions that this works. Okay. All right. So questions about this? This is kind of like the fundamental theorem of Tomita-Takasaki theory, which is modular theory. So this is the fundamental theory of modular. Okay.
So these are like
yeah.
functional analysis.
Yeah, often complex analysis is used for this guy. It's not ridiculous. Like it's something you can sit down and understand, but it takes some time. And it's obvious what the theorem should be, right? You knew what the answer was be just by looking at the finite dimensional case. So it's just a matter of. Okay. Other questions? Okay. Yeah. Yeah. Delta to the IT is not in the algebra. Okay, so again, with all of these things, my crux will be to go to the finite dimensional case, right? And remember, we wrote down delta in that case. It was this delta to the IT, was the density matrix, and then it was sort of multiplied by the right density matrix to the minus IT. So this is in the algebra, this is in the commutant, so it's not in the algebra. Now, of course, when you compute this flow here, this thing cancels because it's unitary. It sort of passes through, it's in the commutant, so it passes through A. It just kills itself. And then you just get this. Okay. So that's why it's clear in finite dimensions. Yeah. Okay. Yeah. Why is it called modular theory? Great question. I don't know, actually. Is the what? The modulus of the, maybe, yeah, maybe that's right. Yeah, that okay, I didn't, yeah, maybe. Okay, good. So, so now another important thing is a characterization of this flow, alpha t. Okay, so we have the following sort of really nice result, which is if you have some, so this is called an automorphism of the algebra. If you have one of these, this alpha t that maps A to A, and you have a one parameter family labeled by this t in R, and it satisfies the following properties for my state. So I can state these properties without reference to the purification. If rho leaves if the expectation values of operators A are left invariant by this flow, and 2-point functions, which you get by feeding in two operators, but now you just flow one of them, satisfies what we might call the KMS condition. So the KMS condition in this form is the statement that this function, so this is a function of t, this thing has an analytic extension to the complex strip. So t, so we sort of define this complex strip S, and if I look where S is t is real, right, down the bottom of this strip, then the function here is equal to the original function, alpha t a b. And then if I look on the top of this strip, I get a similar function, but where I flip the order of b and a, t of a. Okay. And so this is at S is t plus I. Okay, so you go up I in the complex plane. So this is I. And then you find this function where I flip the order of the operators. Okay? And so, yeah, so this is known as the KMS condition because it's the same property of thermal correlation functions. So if I think about 2-point functions of operators in a thermal quantum system, it has this analyticity property. Okay, and you know, yeah, So in particular, where does that property come from? Well, when you check it, a basic ingredient is using cyclicity of the trace. Okay, so the trace in this case, like the thermal case, the state is trace e to the minus beta h up to some normalization. Let's say we're just in a sort of type 1 setting, and then we put our operators here, and we time evolve our operators. Okay, so we just apply time evolution, and then you get the same analytic function. Of course, we have to set beta to 1 to get that to work. And so in particular, this is like exactly what you get for thermal correlation functions, where now we use modular flow instead, right? So and of course, yes. Oh yeah, up to 2 pi. Yeah, there's some pi's here. It probably would be 2 pi if anything. But yeah. In this case, like this analytic function is I. Okay, so the way I've defined it, it's I. Okay, now comparing to the thermal state, yes, depends. These are two conditions, yeah, two conditions. Well, yeah. So this is, yeah, if you set beta 1, then you sort of get this. But yeah, two conditions, and you know, like if I put time evolution here, like it's sort of clear that in this case the modular operator is this is related to e to the minus beta h, and then something on the commutant. But then the flow will be sort of complex powers of this, e to the ITS, so that's just time evolution. Okay? So time evolution is this modular flow in that case. But it's important to emphasize that this thing is true now for any state. It could be some non-equilibrium state. The only thing you have to do is do this weird modular flow instead. Okay? So it's like a non-equilibrium KMS, non-equilibrium version. So the regular KMS T is 0? No.
Little t.
Oh, little t. Yeah, usually the actual KMS is T is 0, but you get this full analytic function there. So.
But when you say non-equilibrium, you're referring to the fact that little t is...
No. Sorry. I'm referring to the fact that the state need not be a thermal state.
Oh, I see.
Yeah.
Where does the beta equals 1? I don't understand what is happening when you measure
Yeah, so that is where if you like, to some extent, applying delta to the 1/2 takes you from A to the commutant in expectation values. And so if I do that twice, I get back to myself, right? Of course, you get back to yourself up to a flip. So the I is coming from the fact that it's delta to the 1. So it's the way I've normalized this. Delta to the 1 is important. Okay, so we can derive it time. Yeah, it's like a 2-line derivation, this KMS condition. So you'll see it from there. It just follows from the definition of the modular operators, essentially, and some of the things we derived there. The psi, right? So this thing, if I then analytically continue it, T to I plus S, and that's something you can show you can do, which I won't go through, then I just get I here, this is minus IT, sorry. Okay, so here what I've done is I've put in this, which is delta to the ITA minus ITA, and use the fact that this annihilates the state, right, psi. So I've canceled that delta to the IT, and I just have one delta to the IT minus IT. And then I go up to I. This gives me powers of delta to the 1/2, 2 powers of delta to the 1/2, so I'll write it like this, as an inner product, delta to the minus IS, B psi. And then I use the fact that, and then I can use the anti-unitarity of J to put in J's here. I just have to flip the order. J. Right, and now I have my defining relation for modular theory. So this just gives me A psi, and you can do the same thing here. You just have to be careful with this IS. You do that, you get delta to the minus IS, B dagger psi from J delta to the 1/2 here, and here you just get A psi. Okay, and so this is just psi B, A psi. Right, and so that's we started here, and then we flip the order. And of course, the flipping of the order is, you can think of this from the cyclicity of the trace. Here, I didn't mention the trace because I'm doing this in general von Neumann algebras where there's no trace. Okay. Now, I said this was a characterization of this flow. In fact, the real statement is, okay, if this is modular flow, these are true. But if I have some automorphism like this, and these two things are satisfied, then it is modular flow of this state. It's an if and only if statement. So this is very useful because you might be able to prove these things for some flow that you don't know is modular flow, and then you learn that it's modular flow. Okay, so yeah. No, you can, because of this. So A dagger psi is in the domain of delta to the 1/2, and B is in the domain of delta to the 1/2. No, but this is all A and B are in A, and that's it. Not for a dense set, it's just for any. it's certainly true if you try to extend this to other states in the Hilbert space, then this won't work. This is really only for these operators. Yeah. Okay. All right, let's move on. Okay, so good. So there was some, yeah. So once you have these modular operators, it's useful to do a few things. So one thing you can define answers this question by Matt. It's something called the natural cone, natural positive cone. So this is some subset of the Hilbert space. It's a cone in the Hilbert space. It's some cone like this. It's particularly nice purifications. It's a set of nice purifications. So it's defined as follows. You take delta to the 1/4, act with a positive operator on psi, and then you take the closure. Okay. And so it turns out that if you take any vector in this cone, the modular, the J for all of these vectors are the same. J are all equal for any eta in here. Okay. So that's quite a useful thing. What's the intuition behind this? Well, again, finite dimensions. So we go to finite dimensions, we ask what this is. This thing, if you go to this canonical purification picture, looks like this, delta to the 1/4, A plus, delta to the 1/4. But these things are just positive matrices, right? So this is a positive matrix, right? So any positive matrix, if D is invertible. And so this cone in this case, where the states in this canonical purification, which remember was this sort of vector of operators or matrices, were our sort of vectors. These are special states because they're positive matrices, right? I could have any matrix that's a state, but positive matrices are special, and they all induce the same sort of J and so forth, and they're this natural positive kind. And this is used for various things. Yeah, and we'll actually use it in a little bit. Yeah, different delta, yeah, different delta. Because like the density matrix is different, right? Like it's just this, like, yeah. Yeah. But are there other like yeah, yeah. So in general, let me make a general statement. I think yes. For let's see, for all normal states, rho, there exists a vector in the natural cone such that rho is eta is a purification. So eta is a purification. So eta is in the natural cone. Right, and so this is a true statement. And then of course all other purifications you get by unitaries on the commutant. So if I act with a unitary on the commutant, I go outside of this cone, right? And so I get other cones associated to other cyclic and separating states. This need not be cyclic and separating, by the way. This statement is still true. Yeah, so this is useful to know because now I can always find a purification of any state that I like. Okay? And I can work, yeah. Good. What's that? It's a good question. I mean, so if you, okay, one point is if you open up a book about von Neumann algebras, they might start and say, suppose I have a von Neumann algebra in standard form, and then they'll write these 4 things, and that's what their starting point is. So this is the natural cone that I just defined. And you can sort of define a representation of the von Neumann algebra in this sense, and you don't have to refer to a specific cyclic and separating state. Right? So it's sort of like blind to the specific state that you're interested in. So that's sort of one use. And so this is called the standard form. Standard form. Yeah, it does. Oh, that's a good question. Apparently not. It doesn't fix the standard form, apparently. Yeah, that's a good question. I think it probably does, right? Yeah, but it may not be a modular operator. I think that's the point. So I think, yeah, so just saying I have an anti-unitary operator may not be sufficient. Yeah, I think that's what it is. So even with this statement, I don't think it's sufficient. So you have to add this. I think that's right, yeah. Yeah. Yeah.
This code contains all the vectors in this code are cyclically separated.
No.
Then how do you get J for each?
Yeah, good question. So you don't really. So let me just say J are all equal for any cyclic and separating.
Then what is this density matrix D order A?
Yeah, so this is in finite dimensions, right? So this is like, you know, I didn't want to do the calculation, but if you just do this in finite dimensions, right, you have sort of d to the quarter, d to the minus quarter acting on the right, and there's a d to the half, so they combine to give you 2d to the quarters here. So this is the version of the canonical cone in finite dimensions. Right? And it's just positive matrices. This is just a weird way of writing it. It's important in general to write it like this. It's like the music notation. No, it's not a sharp, it's natural. Natural, right? So there's a sharp cone and there's a flat cone, and they're different. And this is the natural one. Yeah. Yeah. Okay. Good. I'm going slow here. Okay. Yeah. Yeah.
Which we might.
We may or may not find. Yeah, we may or may not.
Are you not saying now that if by this construction here that if this is a normal state that I'm starting with, then in fact I will find such a psi, and I call it eta.
If you're in standard form, which means that there exists one cyclic and separating state. So if there's one cyclic and separating state, you can always find a purification of any state. There may not be a cyclic and separating state. That's the statement. Okay. So yeah. So it's useful if there is, and then you can always find purifications. Yeah. Okay. Yeah. Sorry. Yeah. Okay. All right. So a final thing here is that at this point we have modular operators. So I can mention a further point, further classification of type 3 von Neumann algebras. You might have seen, you know, this sort of 1 or sometimes this lambda that sits there. This lambda relates to modular theory. And so one way to define it is if I take the intersection over the spectrum of the log of delta for all psi's cyclic and separating for A. Here I need to be in this standard form, but that's okay. So this is the spectrum of this operator. If I take the intersection of all of the possible spectra, then I get some possibilities. In general, it's going to be some lattice subset of the real line. So I could get integers times log times some number. N is Z, or I could get everything. So it's a continuous spectrum. And so this case is the 3 lambda case, and this case is the 3-1. And you can choose to ignore this case for now because I don't know of any physical application. It might come up at some point, but this case is the interesting one. This is the quantum field theory one, and we'll see it sort of follows because of this continuous spectrum for this modular operator. Okay, so this is saying that all states, every state you can imagine, the modular operator is continuous, has a continuous spectrum. Okay, and yeah, good. Yeah, good. So in the type 2 case, you have a trace. So in that case, the modular operator, yeah, so the modular operator is actually a product of 2 operators, one in the commutant and one not in the commutant. So that doesn't happen in type 3, but in type 2 it does happen. And there are states where the spectrum is just flat because it's a trace, right? So it's, you know, it's like the trace, like for type 1, for example, the trace is, you know, trace times the identity. So the spectrum of this modular operator comes from the spectrum of this identity. It's the difference of 2 things. So in general, you'll just get 0. That's right. So because this is the intersection of over all possible spectra, in the type 2 case, you just get 0. Because there's one state where the spectrum is just 0. Yeah, I think that's right. You have to generalize a little bit to allow for yeah, roughly delta is the identity. Yeah, that's right. Good. So, good. Now, I wanted to say a little bit about relative entropy, because we'll try to use that later. So let me say something about relative entropy. Okay, so relative entropy is some notion of distance between 2 states, right? It's some comparison, it's a way to compare 2 states. We heard about it earlier on this week, at least in the classical case, but there's a quantum version of relative entropy. And in particular, it relies on 2 states. So we need 2 states, rho and sigma, right? So again, they're like these linear functionals, normal, and so forth. And what I'm going to do is I'll just assume they're faithful, and that I can find, and then that means that I can find 2 purifications that are cyclic and separating. And in particular, I will use these purifications in this natural cone because it simplifies things a little bit. So then what I do is I define a relative version of modular theory. S so we define this S operator, but now it refers to 2 states, so I'm going to label it with sort of with a label phi inside. It's just a label here. And it's different to how I defined it before because now there's 2 states. So when I act with S, I go to this other state. Okay? Sorry? They don't, it just simplifies things. I'll tell you when it simplifies things. So this is the, you know, that definition of the relative modular operator, and it looks very similar to before, but yeah, it's different because I have 2 different states here. And so you again go through the closure and so forth, and you show that there's a polar decomposition, and in particular, because they're in the same cone, this J is the same J. That was kind of the point. So you get a J here, and a modular operator, which is now this relative modular operator, okay? And then, given that, we can define Araki's version of relative entropy, which is just the expectation value of log of that modular operator. So in particular, so we say, you know, the relative entropy of the two states really only refers to the states, rho and sigma, but we use the purification to define it, is psi log delta phi psi. So it's the expectation value of log of this modular operator that you get here. And yeah, just to remind you, rho and sigma are purification, like phi is the purification of rho, and sigma is, sorry, I didn't use that notation, psi A, and sigma is phi A. Right, so that's how they're related. And so yeah, this is Araki's definition. And you know, you can again, as usual, go to the type 1 case with matrices and so forth. Psi gets replaced with this canonical purification, d to the 1/2, the density matrix to the 1/2. Phi is the density matrix to the 1/2, like this. And then the relative modular operator, it's not hard to see, is the density matrix for the algebra on phi, and then the right action, which is the commutant for psi, right? So remember the modular operator, when they were the same, had the two same states here. Now we have two different states here, okay? And that's not so hard to see from these definitions. You can just check it. And so then we go ahead and compute the relative entropy, and you'll find the answer. It's not hard to see. That's not right. And so this is the usual definition of the relative entropy for density matrices. Okay, all right. And if they were both diagonal, this would just give the same definition you saw before. Okay, good.
So is that delta phi psi?
Yeah, it's positive. Because it's the product of two positive operators that commute. This log here?
Yeah.
Well, the log makes it not positive.
No, I'm asking the delta phi psi.
Oh, yeah, it's positive, yeah. Yeah, this is this polar decomposition. It's positive operator, by definition. Oh, sorry. Yeah, it's invertible, so it's, yeah, it's positive. Definite. Yeah, I think it's positive definite. Ima? Is this positive definite, the modular operator? I think it's definite. It's definite, right? Yeah. Okay, thank you. Yeah. Okay, so one of the most important things about relative entropy is yeah, well, I assumed that this was faithful, right? Well, yeah, that's right. Oh, yeah, you're right. Yeah, you're correct. If it wasn't cyclic and separating, you can define these things, and then it's not. But that's the only case, yeah. Of course, this is always defined for density matrices, right? Sorry, it's not always defined. Yeah, so it could be infinite. Yeah, there's some condition on the spectrum of the density matrices, which I forget, so I won't try to remember it here, but yeah. For now, this is well defined because I'm in this faithful case. Okay, so one of the most important things about relative entropy is it's monotonic in some sense, right? So in which sense? So monotonicity of SRL. There's a more general sense, but this is pretty good. If I take a von Neumann algebra, subalgebra of my original subalgebra. Okay, so this is a sub-von Neumann algebra. Then you can show that the relative entropy, which I'll write in terms of the purifications now, for B is less than the relative entropy for A, where my notation is that the relative entropy, this thing is equal to the relative entropy of the states restricted to B, and phi restricted to B. Right, so these defined states, they're linear functional. That's the context in which I defined this relative entropy. So that's just to take that back here. But now we can restrict to either B or A, right? We just have the same states on the Hilbert space, and then we just restrict either to B or A, and you get this inequality, okay? So this is really important. It's sometimes called data processing inequality. And it makes sense if you think of relative entropy as some distinguishability measure. You know, if you have less things to distinguish the two states with, it should go down. Of course, establishing it as a distinguishability measure is, you know, is sort of equivalent to showing this inequality. So the proof is actually very non-trivial, yeah? Yeah, it's the B and the A, right? So I defined this as the states restricted to B on the left, and these are the states restricted to A. So they're different states if I look at a smaller thing. In finite dimensions, this is like taking a partial trace, right? But yeah, they're the same. They're the same. Psi is a vector in the Hilbert space, a purification, right? And I can take that vector and I can restrict it to the subalgebra B or A. When I restrict, I get different states, and so this is different. Okay, so this is the difference here, the B and the A. Yeah, you just take expectation values as you usually would, and just say, oh, I'm only going to feed in B here. Operators of B. That's all it says. And you get different states. They're just different states. Okay. So yeah, maybe this is like, yeah. So you would be happy if you did, probably many people would be happy if I thought of this as some partial trace on density matrices, but I can't do that in von Neumann algebras. So this is what we're left with, okay? All right, so the proof of this actually just follows, you know, these are expectation values in the same state, and so you just have to show that the log of the relative modular operators defined for A is less than the log of the relative modular operators defined for B. It relies on this. And this, you know, okay, this is rather difficult to establish, but you know, you can establish it just by thinking about the definition of these operators, right? So they're sort of, yeah, they're sort of defined, yeah, right. Okay, let me not say any more. Yeah, so now because I have two algebras in the game, I have to label my algebra. Before I didn't have that, so I just didn't. But yeah, the definition of these operators, I didn't actually say it, refers to the algebra, right? So this definition depends on the algebra, so I just use a different set, okay? Yeah. Sorry, this is the definition, right, of these operators. Yeah. 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 That's right, yeah. So you define them on the total Hilbert space, but you define them with respect to the algebras, yeah. That's right. It relies on this. Okay, so this is a little tricky to establish, but once you do, then it follows. But yeah, so this general property of modular operators is true when you sort of restrict to subalgebras. The modular operator actually increases. The log of the modular operator increases. And so that's sort of important, an important inequality that we'll use later. Okay. Yeah, good. So sorry, this is, I didn't want to say, well, I was going to say this, but then What is the difference between which side? These two things? Yeah. Well, in a sense it does, you're right. So if we go to S, yes, this is what you want to say, right, which I was going to make a comment about. But so S phi psi is defined, remember, on this dense domain A psi, okay? And S phi psi B is defined on a different dense domain B psi. But it's actually, this is a subset of this, and when it acts on this, it's exactly the same, okay? So what you say is this is an extension, one is an extension of the other, this is an extension of this, okay? But extensions need not be the same, so yeah. Yeah, that's right. I mean, because we start with a different dense domain and close, we're going to get a different operator. And in fact, it was different because it's defined on a different domain. Yeah. So it's called an extension, and they need not be the same. But this extension property is actually the thing that lets you prove this inequality. Yeah, good. Good. Now, yeah. All right, so I think I have to move on. Yeah, maybe I'll come back to that if I have time. Okay, so I'm not going to talk about co-cycles. So we're going to move on just because I'm going to run out of time otherwise. I'm now going to switch gears quite dramatically and talk about algebraic quantum field theory. Okay, so I guess maybe I'll ask if there's questions before I do that dramatic switch. Okay, so, all right, so let's think about algebraic quantum field theory. So let's start with what we might expect of quantum field theory. In particular, I'm just going to simplify things, and I'm just going to think about a scalar field. So we have some scalar field for X that's an operator, maybe, on H, okay? Where X here is some point in Minkowski space. So I'm thinking about quantum field theory in Minkowski space, okay? Now, it turns out that phi of X is actually not an operator. Right, so your local quantum field that you're used to is not actually an example of an operator. It's not even an unbounded operator. Right, and so why is this? Well, if I take phi of X and I act, say, on the vacuum, right, and I compute its norm, I get a two-point function where the points are the same, coincident points here. So in general, this is infinite, okay? So in fact, on all states, or many states in the Hilbert space, you can show this. So that means it's never going to be defined as an operator or an unbounded operator. At best, you can define matrix elements, right? So matrix elements are well defined. And so, you know, this is how you should think about the local quantum fields. Now, you can ameliorate this problem just by smearing the operator. So if I take phi and some function f defined on Minkowski space, on some region of Minkowski space, and I integrate it, and f is sufficiently smooth, in the support of some region R, the support of f is in R, then this is a good operator. It's an unbounded operator though. So you know all of the discussion that I said about closed, densely defined, it's the same thing here. Okay. So this is sort of a fix. So if we're trying to fix this issue, the first thing we do is we smear. And then the second thing we do is, well, we have to make some assumptions, or sometimes we can show, depending on sort of our exact starting point, that there exists some dense domain, H, let me call it H polynomial, where polynomial polynomials of these smeared operators is well defined. And if you also assume this is true for the adjoint, which is natural if you think of, say, this is a real scalar field and you have real functions, then you can show it's closable. And then you can do the things that you like to do with usual operators. So in particular, we can do something called functional calculus. So we can take functions of these operators, right? That's fine. I can take a function of an operator where f is bounded. Some bounded function. So a function that doesn't go off to infinity, it has some cutoff. Okay? And then you show that this is a bounded operator. So we always wanted our operators, when we talked about von Neumann algebras, to be bounded. So this is what we do. We first smear, and then we take functions, right? And there's some assumption that goes into that. Now we can finally define our von Neumann algebras as just A, some algebra of operators with reference to some region, R. This is going to be some subalgebra of all possible operators on the Hilbert space. So remember, this is defined on some Hilbert space. And it's defined as just some union over all of these possible bounded functions, all of these smearing functions with support in R. Phi of F, that's some set of operators. In fact, it's a star set because if this, if I take the complex conjugate of these, I can make it into a star set. And so then I can take its double commutant and guarantee it's a von Neumann algebra. All right, so this is like the weak closure, remember? So this is the von Neumann algebra associated to R. Okay. Now, R, for sort of technical reasons, we take R to be some open region in space-time. Right, and so the other thing to say is, why did I take the weak closure? I could have done other things. I could have taken this C-star closure. There was some physical motivation for that, right? Like that's the kind of things we could compute, were matrix elements of these operators. Sorry, we could measure in some experiment, were matrix elements, the norm, not so much. Okay, so it's natural that we could we should sort of allow for the closure of that because we can measure anything to some good approximation in the closure, okay? And so that was the motivation for that. There's also like some extra motivation that comes from causality. So let's go through that now. So let's think about some consequences of this definition. Okay, so let's draw a region. So we have our region called R. This is some space-time region. And so I have some algebra of operators associated to that space-time region. Now, there's something I can associate to this set, which is a little bit like the commutant, so it gets the same symbol. But it's everything that's space-like separated to R. So everything that's space-like separated to R, I'll call R prime. Right? So the exact definition is that R prime is the largest open set space-like to R. Okay? And so, pictorially, that's what we would get if we took this region R. R prime would be this sort of unbounded sort of light cone region out here. Okay? Okay. So now if I take sort of functions over here, right, with support in R prime, and I smear operators with bound, and take bounded functions of them. So now f here, we'll call it f prime. Support of f prime is r prime. So this defines some set, some star set of operators. Then by causality, sort of Einstein causality, this has to be in the commutant of AR, right? So remember, AR was the operators associated to R, or at least the weak closure of those. And if I take the commutant of those, then the commutant of those should include these operators. Okay? This is not an algebra, but because it's a subalgebra of a von Neumann algebra, I can take its weak closure and still have the same equation. Okay? Right, because this is like the smallest possible von Neumann algebra that contains this. So that has to be true. So, so that gives the following equation. We find that A of R prime, the algebra of operators associated to this region, should be inside of A of R commutant. Right, so this is the commutant. This is the sort of space-like separated region. But there's some sort of correspondence between these two that seems natural. This is called Einstein causality. Okay, so what we've described here is some map between open regions and algebras. And this is sort of often the starting point for a study of algebraic quantum field theory. Okay, we started in a slightly different place because you're familiar with local quantum fields, but often, or not always, you start with this and then you just try to build some consistency conditions on these things that sort of mimic what you would expect from what we started from here. Okay, and that's powerful enough to constrain many things about the theory. You have to put some really reasonable things in and you get a lot of things out. So that's sort of the starting point for the success of algebraic quantum field theory. Okay, so what are the things we might want to put in? Well, this is yeah. Yeah, because everything else is smaller, right? Yeah. So it would have, yeah. Yeah. Yep.
Sir, R prime is outside the light cone, right?
Yeah, so it's outside the light cone of R. Come back to you.
So how can A of R prime be a sub-algebra of A of R?
It's not a subalgebra of A of R. It's a prime here. So remember, these are all the operators that commute with A of R, right? And so all the operators that commute with A of R are outside. Right? Well, there are some situations, and I'll mention them, but not yet. Okay. And you're correct. It's yeah. So I'll come to that. Okay. So yeah. Well, I said that it's the largest open set, so the answer is no. And that's just for some like consistency, right? So if I did include it, then there would be an intersection between these two, and maybe we don't want that. Yeah, so the assumption is this works without a UV cutoff. Now, you may not like that assumption. Some people don't, I think. But that's the assumption. So we're sort of working in the continuum directly. Yeah. Good. All right. Now, and my philosophy on that is that maybe ultimately we always have a cutoff, but this is some good approximation, and we get really good results out of this, thinking about it from this point of view. So that's kind of my point of view on that. Yeah. This thing here?
Yeah, when I think about the closure,
Yeah. Yeah, so it's on the full H. No, sorry, this is like a von Neumann algebra closure. So it's on all the operators. So it's on B of H. Yeah, so as I said, yeah, good. So yeah, so maybe let me say it here. Yes, this is where these are defined. As soon as I take bounded operators, it's defined on the full Hilbert space. Okay, good. So yeah, right. So now we start here and we add some postulates. Obviously, this is one we would always want to have. We can also have some other ones that's completely fine. When R1 is inside R2, this is solid. Another one that we might want is, as Finn was asking, maybe this is a maximal thing. So that means that A of R prime is equal to the constant. And this is also quite reasonable. This is called Hague duality. At least visually, it seems reasonable. And it's probably true. So there's some uncertainty in all of these axioms, but it's probably true for connected regions. Seems to be my impression, at least. Connected regions. And it's definitely been shown solidly using really reasonable things. It's actually proven for diamonds. So special kinds of regions, which are the intersection of the past and future of a point, in a CFT. Diamonds in a CFT. And so, these are connected, so that's fine. And there are interesting violations in theories with charges, in the presence of charges, charged operators, and disconnected regions. So if I had two diamonds, for example, so this is my R, right? So R doesn't have to be a connected thing. It could be two things like that, and you find violations in the presence of charges as long as you think about the algebra of neutral operators. Okay, so that's some thing you can do, and then you get violations. And they're interesting violations because they sort of start to try to classify these charges, and this is this work by Horacio Cassini et al. There's sort of many papers now trying to connect this to charges and then higher form charges, things like that. Yeah.
If the region is not causally convex,
Yeah. So another thing. Yeah. So good. So yeah, I don't think there's a huge distinction between those two, but that's something you would try to understand. So that's another reasonable thing I was going to add, which is A of R double prime is equal to A of R. So what is A of R double prime? Well, let's go to our example. R prime is out here. R double prime is this guy. So it's the causal completion of R, right? So it's very much like the von Neumann algebra is the completion of some algebra. R double prime is the completion of the causal set. And so this is a reasonable thing. And in fact, it follows from Hague duality for all regions. So, it's probably true in many situations, but here are some examples and counterexamples. Okay, so one example is if I take a region like this, sort of a time-like region. Okay, so that's R. I could easily smear my fields here. That's totally fine. And then the causal completion is this diamond here. Okay, and this statement has a name. It's called the time-like tube theorem, if it's true. Time-like tube theorem. And indeed, it does seem to be proven. It's been shown very generally by Witten and Stromier using some, even in curve space, using some analyticity properties related to things I'm going to say in a little bit. But yeah, so So this is reasonable. Here is a counterexample. If I take two diamonds that are time-like separated, okay, in free theories in even dimensions, due to Huygens principle, and I'll let you think about why that is. But this is the region R, and my causal completion would be this diamond here. And yeah, so because of like Huygens principle means things are sort of propagating exactly on the light cone, and because of that, in free theories, you can have a violation of this. This counterexample seems kind of silly, right? I mean, it's free theories, so it's plausible. You add interactions and it goes away. So it's still plausible that something like this is true, at least for reasonable theories like interacting theories. Yeah. Yeah, time. Yeah. Yeah.
I mean, I don't understand if I have an operator which is out there in the wings, are you saying I can express that in terms of operators in R by this?
This guy here?
So if I have an operator which
Yeah, you can. Yeah.
that is expressible.
Yeah, I guess like you're doing something, you're basically doing some kind of space-like evolution of the, if in a free theory, for example, you want some space-like propagator, this is what we do in ADS-CFT. This is the causal wedge reconstruction. So you know, you can sort of explicitly do it in some cases, and yeah, and there was some initial work a long time ago doing this. There's a more general argument. Not happy. All right, Nima wants this. Yeah, you're correct. Yes, thank you. Massless. Yeah, thank you. Yeah, question. Yeah, it's just the region is these two sort of diamonds that are time-like separated, and the causal completion would be this thing. Well, actually, I was trying. It's a homework problem for you to think about it. I think it's violent. This is not true. Yeah. Okay. Yeah. So you want me to finish, like now? Okay. Yeah, I can finish now. Yeah.
Okay, maybe I just ask a quick question. So the counterexample is with disconnected regions, right? Is it true that if you just had a connected R, like there would be no counter? Is it known that?
Yeah, I guess that's sort of roughly what's going on here, but I guess you could think of some other weird connected thing that I don't know the answer for. This has to be some kind of, you know, roughly a tube. So like you have some observer here, goes from these 2 points, and you just thicken it.
Yeah.
And then you can continue to thicken it to the causal completion.
Matt?
You're using analyticity?
Yeah, you use analyticity. Yeah.
Actually, my question was about the first thing, that A of R1 is A of R2. Isn't it true that there are counterexamples to that? Like if you have a gauge theory without charges and you consider a region that has a hole in it, then you can have like the total charge operator, but then if you add the hole back in, that's actually not an operator anymore because by Gauss's law it has to be 0, stuff like that.
So you add the hole back in.
Yeah, so that adding in something actually reduces the size, actually removes operators. I thought with gauge theory there's like counterexamples to this principle.
But you want to do some kind of Gauss's law on a sphere that's contractible?
Right, so if you don't have the hole, the algebra includes like a total charge operator. But when you add the hole back in, there's no such operator because you know the total charge is 0. If your theory doesn't have charges.
I think.
Or you can do like
I think
the
it's
magnetic
somehow.
field if you want.
Yeah, I haven't thought about that case. So yeah, I don't know. This I would not want to violate this. So in that case, I would try very hard to get around that. I don't know how, but I would really try to get around that. Yeah, I mean, I guess if you add charges, then yeah. But I would guess that there's some way to get around it. But, you know, these were defined in some way additively, right? So I sort of like started with things and I built them up. And so it sort of follows from that. So I think maybe if you define your things additively there, you'll sort of just remove that operator in any case. Now you might want to add it for some other reason, but I would say don't do that. If you want to have this sort of set of axioms. Yeah. So that one should be fine. So yeah. So I would want, yeah, use these sort of additive algebras, and then that will be the case.
Maybe the issue is that in this setting, we're assuming there isn't an ambient. Everything is like subalgebras of there's like a fixed ambient space.
Yeah.
Maybe that's the.
Yeah. Well, if you're not doing that, then yeah. You're saying because there could be a hole. Is that what you're saying?
You could associate an algebra to just regions of, you know, to just Lorentzian manifolds without specifying.
Yeah, but we don't do that, right? So we start with B of H, right? So what is H? It's the quantum field theory on the manifold of interest.
Well, not if you
So
algebra.
well, yes. So then we can start talking about other abstract things, but that's the point that I'm working from. So yeah, so you can ask this question maybe in like C-star algebra sort of versions of algebraic quantum field theory, and yeah, maybe that's an interesting thing. Yeah, usually you're at best at this point working on some fixed manifold, and even then it's like, yeah, some of these sort of principles it's hard to see like how the same quantum field theory on two different manifolds are related. So that's an issue, one issue that people try to address, but yeah. Yeah, so I can talk about that for 10 minutes, but no, I won't do that. Yeah, no, I will talk about the type, yeah.